maybe a short introduction. I'm a mechanical engineer. I'm not an aeronautical engineer, so that's already a bad start, right? But after a few years working on gearboxes and so on, mechanical calculations, I designed a car in my free time, which is this one actually, which is now 13 years old. And the concept was based on making it go faster through the corners, which is what you typically want for race cars, but instead of using downforce to push the car onto the ground, which creates more forces, which increases the friction limits so it can go faster, I wanted to use the air directly left and right, because there's a number of benefits. If you use downforce on the car, there's more tire wear, because you use more friction, you're more dependent on the friction coefficient on the ground. You load your suspension, so you need bigger springs, bigger dampers. And as you speed up, aerodynamic forces, they scale with the square of your velocity. So you push the car down and you change your ride height. So the aerodynamics actually influence the car's position, and then that one influences the aerodynamics again. Maybe some of you know porpoising effects in Formula One. It's also a very nice example of interaction between suspension and aerodynamics and so on. So I went to a design agency in Belgium where I live, and I asked them, can you run a simulation for me? And they said, yeah, we can do this for you, but that will be 3,000 euros. I said, well, for a hobby, let's just leave it at that. And for some reason, I quit my job. I went traveling for a few months, and when I came back, I needed a job. So I just asked them, can I just work here? And they said, yeah, that's fine. And 2 weeks later, after coming back from South America, I was just working at this company. And there, I teamed up with the company, and I ran the simulations actually after hours to see what would happen. So it has internal air channels, and if you close them in an asymmetric way and spit out more air on one side than the other side, you generate lateral forces, which is quite interesting. And through simulations, we were able to show that it can actually work. And we teamed up, we got it patented, which is really nice. It was granted, so they thought it was actually a proper patent. And then our patent was referenced to by Ferrari in their patents. And I got to visit Pagani supercars in Italy, which is really, really cool. So that was like a boy's dream come true, right? Super fun stuff, everything I wanted. But in the end, the car company said, like, you're using too much packaging space. So the channels that you're suggesting, they're nice, it works, but it's using up too much space. We can do other things with that. So I left the project and left the car design for what it was, but this was my way into aerodynamics. So for the next 6 years, I did simulations myself and managed the projects for the engineering department at that company. And we did simulations on drones. We did our own carbon layup and made the drones. We crashed a lot of drones. We worked on NASCAR, IndyCar, all kinds of cool stuff. We also did some wind tunnel testing on solar panels, because those things tend to fly away. So we wanted to match wind tunnel testing with simulation data. I learned a ton of stuff about aerodynamics and really got me hooked. But it was always the same thing. So if I go to the first slide, like traditional CFD, what it is about, I don't know, who has done CFD simulations already? Okay, a few people. So basically what you do is, just like you have a physical wind tunnel, you create a virtual wind tunnel. So you take your 3D model on your computer, and then you build like a tunnel around it, like maybe 2 times the car length up front, and maybe 5 to 10 times the car length behind, and then like a big box, so the air can virtually pass over it. Now, in a CFD simulation, we don't have mathematical solutions or analytical solutions to solve this problem straight away. So what we do in CFD is we take very small cubes, which we call cells, and we solve equations for each cell. And the more cells you use, and the smaller you make the cells, the more accurately you can capture a flow. That's what CFD is about. So typically your process is that you would hire an engineer, some of you, after you graduate, who knows how to run simulations or has the capability to learn how to run simulations. You buy a CFD license, so computational fluid dynamics license, typically $20,000 to $100,000, which is quite substantial. You buy the hardware, a computer with a certain number of processors, certain number of gigabytes of memory, and then you start setting up the mesh, which is those cells that I mentioned. And usually you try and max out your computer if you have like 100 gigabytes of memory, maybe you go for a 40 million cell CFD solution, just because you can, right? What you then do is that you have to schedule it on the server, you have to grab the license if someone else doesn't have the license, and then once it's done, which can take hours or days depending on what you're doing, you have to get that data and translate that into performance numbers, like what's the drag coefficient, what is the lift coefficient, or what's the downforce, so the numbers. Also visuals, like you want to understand why it generates downforce or why it's bad in terms of drag. So you need to create visuals that help you understand how it behaves. And then once you have those visuals, you need to interpret what's going on and translate that into design improvements. That's your conventional CFD approach. And it's a very good one, it works. I've done this for years myself. It works if you do it day in, day out, if you can afford the license. It works. People at big car companies, airplane companies, they do this day in, day out. They have streamlined the process so that this becomes easy. But if you're new to CFD, like many of you, but also like many companies, a lot of companies working on products which relate to aerodynamics actually don't look at aerodynamics. There's a lot of motorbike companies out there that have products which are completely dependent on aerodynamics, but they don't do aerodynamic simulations or studies. So for them to get into this, that means spending a few $100,000 because the license alone is up to 100,000, the engineer costs 100 a year, and so on. So I wanted to flip this around and focus on the part that really matters. So in my opinion, what matters is that once you have the simulation data, is first of all to understand what's happening and to improve your design. So if you can automate everything that happens before that point, I think you have a valid product. So Automated CFD, which is AirShaper, the company I founded back in 2015. So what we do is we flip the entire process around. We started off with the concept of saying, we're going to make everything transparent for you. This is a fixed price per simulation, and you can just order one simulation, 2 or 20, whatever you like. It's completely transparent, and we make sure it works for you. You don't have to worry about a thing. The setup is just 5 minutes. We do that for you. That was the concept. So if you want to offer a fixed price, running a simulation costs a lot of money. If you do it on a high-performance cloud, for example, like Amazon or Google, you have to pay for their servers, and this can cost a lot. Like if it costs you $10 per hour and you have to run for weeks, you can imagine it's very costly. So if we offer a fixed cost, that means we have to work out a way to control the number of cells that we use, which is that resolution that I was talking about. Because if you control the resolution, you control how much memory you need, you control how many CPUs that you need, and so on. So we actually work our way entirely backwards compared to the traditional CFD. We start with the cost, calculate the number of cells, and then we tune the mesh according to the total number of cells that we have available. But if you have a fixed number of cells available, you want to do this in the most efficient way, right? I'll get back to that. And that's what we did. So this is our setup interface. This is the only thing you have to do to set up a simulation on our platform. You can choose whether something is on the ground or above the ground, whether it's static or moving. We automatically detect the wheels and apply rotation to the wheels. This is all integrated. You can add radiators with a simple click of a button. You just zoom in on the radiator. You provide 2 points on the pressure drop curve for the radiator, which is a curve that indicates how much pressure drop do you have in function of velocity. And that's it. That's the only thing you need to do to run a simulation. If you compare this to normal CFD processes, this is super fast. And obviously, we take away some of the control. So some engineers will feel very uneasy, like, whoa, I want to control my mesh, what are the solver settings, and so on. So a lot of people panic at first sight, like, oh, watch out. But we actually make the results open to them. So if you run a simulation, we just share the mesh, we share the output data, they can see everything. Then what happens is that once you're done with the simulation, this aspect I mentioned of translating all the data into visuals, something that helps you understand what's going on, we've also automated this. And this all runs in your browser. And you don't even need a heavy machine. We've compressed everything. This runs in your browser. You can look at the underfloor, the low pressure, the performance of Vortex generators. This is all included actually in the simulation, and you can just, with a few clicks, visualize this, share it with other people, and look at the results. So what we see here is that you can play with the streamlines to see how it actually dives underneath a rear wing, for example, how it curls around the front splitter. Yeah, this is a noise module, so it's a rough indication of wind noise. And this one, we also split models into separate components. So you can click on the wing and you know, okay, I have 30% downforce coming from my wing. And here you can look at the radiators just to see what is the flow rate through a radiator. Because very often, you don't have uniform flow through a radiator. It's just like one part is performing well, the other part is actually not doing anything, which means you're carrying too much dead weight because the radiator's not working properly. So that's basically what our platform does. And to make this possible, well, usually the easier something looks, the more stuff happens in the background. We do the same for vertical takeoff and landing or aircraft vehicles. And there it's the same philosophy. We want to make it as easy as possible. So this one, we just set a certain velocity. This is very low because it's hovering. Oh, I set it to 100. And this one has propellers. And propellers is typically also something which is challenging to include in a simulation. So what we do is we use what's called MRF. It's a technique that kind of develops a flow field around the propeller. But just to set up a simulation, again, we've made it super easy. You can just click the components. We automatically detect the axis of rotation of a propeller. And you can set the RPM, change the direction of rotation, and that's it. I myself have made many mistakes in the past when I was a consultant. Like, you come back after the weekend, after 2 days of running, and then, oh no, rotation is wrong or everything. So we try and take away all of the possible errors that you can set up during a simulation. And once this one is done, you can see super interesting flow structures. You can really see how the swirl of a propeller goes down, how it interacts with the frame of the airplane itself. So all of these things can be analyzed online. And of course, there are loads and loads of different accuracies and types of CFD and so on. And we're not claiming that we are replacing everything, but we are claiming that we are super fast at generating insights in a matter of hours compared to weeks in other cases. One of the cool things as well is that we can work with 3D models which are, well, basically crappy in some cases. So very often to run a simulation, your 3D model needs to be perfectly closed. There cannot be a single gap or hole or an error in the surfaces, otherwise your simulation just blows up. And we've made our platform compatible so that you don't have to do this, which again makes it a lot easier for people to work with the platform. And in this case, because this one includes propellers, we'll now go to what is called elements, where we can actually click on a propeller and see the airflow going through. So if I just wait for this one to appear. So the propeller, we automatically create streamlines that go through the propeller. You can see what the downwash is, where it goes to, how much torque, how much power is required, and so on. So again, we made it as easy as possible to run simulations. Now, that's the nice visual stuff. If I go into the boring bits, just for a brief moment, don't fall asleep, please. The first thing I want to discuss is adaptive mesh refiner. So I mentioned that we aim for a fixed number of cells for your simulation, right? Otherwise, our costs will skyrocket. So that means you want to use the cells in the most efficient location that you have. And if you compare this to taking a picture, if you want to take a picture of something which swirls or a spiral or something, you cannot see that spiral if your pixels are bigger than the spiral itself. That's quite logical. It's the same for CFD simulation. If you want to see a vortex structure or a swirl of a flow, you need cells which are small enough to actually capture this effect. Which means that far away from your vehicle, the flow is just moving nicely along, not much is happening. Which is why far away, you see these big blocks. Those are big cells, because nothing is happening there. It's just there to provide enough room for the air to pass, so don't have too much blockage in the wind tunnel. But as you get closer to the vehicle, you will see more and more effects locally. You will see that as it goes around the front wing, for example, it kind of just jumps up, there's high pressure gradients and so on. So what we do is that we start with a mesh, which is already nicely refined close to the object, with smaller cells close to the car. But then we run a first simulation, and then we will automatically analyze the results So we have algorithms that look at the flow structure. They look at where you have high speed-ups, for example, high gradients of pressure, where you have high vorticity, which is like swirl and curl in the flow. And we automatically refine the mesh locally where it is kind of struggling. And then we refine the mesh so that we capture more details there. And that is why in this picture, you see that the wake of the car, in this case, this is a dummy Formula 1 car, it really kicks up the air. And in this kick up, you have a lot of things happening in the flow. And automatically, you see that the mesh is being refined there. We want to capture more details there, because if you capture more details, we will capture this aspect in a more accurate way, which improves the quality of the output without adding too many cells. So adaptive mesh refinement is something that we created in-house. Well, there's a lot of softwares that do this, but we created it for OpenFOAM. And if you use OpenFOAM, by the way, we made this open source. So you can actually download this bit and start playing yourself with it. And this is on the surface, for example. So you can see there's different grades of mesh depending on where you look at the object, because some areas struggle, some areas don't. Now, a second thing is convergence detection. If you run a simulation, what happens that instead of solving all of the equations at once, that would be very expensive. What happens is that you start with a guess for your simulation and you iterate your way through the solution until you converge to something. Now, you can just go for the easy way and say, let's go for 10,000 iterations. That's usually enough, and then always apply that one. But that means you're just waiting for too long, and this will cost you a lot in terms of cloud computing resources. So for us, because we offer fixed pricing, it's very important that we control the number of iterations, which means that as soon as it's good enough, we have to stop. That's the basic philosophy. But good enough really needs to be good enough. So imagine this blue curve is your force. So on the x-axis, we have the number of iterations. I should have put something there. And on the y-axis is maybe your drag force, for example. So in the beginning, you can see, okay, this is not stable at all, right? And then as you enter the yellow bar there, we can see that the line is quite flat. So that means if it's flat enough for long enough, our algorithm will say, okay, it's now converged, which is point A. And after the simulation has converged, we will still continue to run the simulation because you can see it still goes up and down a bit. If you stop at a peak or at a low, for example, it could be that your vortex or your wake stops in a certain position, which is not the full picture that you want to see. So we continue the simulation to average those variations in the flow so that we have a reliable averaged value. We run steady state simulations, by the way, but still you can have like pseudo oscillations in your flow. So once we've averaged for long enough, and we also do this dynamically, depending on how many oscillations we see, we stop the simulation, which is the green dot at the end. What can happen sometimes is that during this averaging, suddenly it goes up again, and then we just kick out of the system and wait again for it to be flat for long enough, and then again detect convergence. So all kinds of mathematical tricks to actually make sure we wait for long enough, but not for too long. That's the basic concept to save costs. Another cool thing, I hope this works. Nope. Okay. Should be a video playing. The PowerPoint. Oh. Huh? Okay. It says internet is not working. Let me just check for a second. No. It says it has internet, but it's not working. Okay. I'll go back to this one then, maybe. What was the button to switch?
No, it's already. PC.
Control, please.
Try again. Try to log in. See what happens. Maybe it kicks me out.
Is this keyboard?
Yeah, try Alt, whatever.
Control Command.
Yeah, press it. It will kick you off. Kick me out.
Where is Alt?
I'm not a PC guy. And I have my glasses. That's my problem. Yeah, you got it. Okay. Yes,
All right. Cool. Nice back. Now let's see if it works. No.
yeah, same problem.
Okay. It works. This.
Oh, good.
Yeah. I actually need a new one. Sorry. Is this the right way? Yeah, I bought it already. No.
It's you, bro.
Yeah.
It's you. It's you.
I'll get tired of it soon.
It's you. It's you.
So, do it like this. So, Aptera is a solar car company here in Carlsbad, actually, north of San Diego. And what we did for them is not just to analyze the flow, which is what you see here. So this is an analysis of the flow. These streamlines actually came directly from a CFD simulation that we ran. So what you see is the streamlines, then we show the coloring. This is the speed that you see. Then the red clouds are the source of drag that we saw. And then this is the pressure map. And then we asked our software, please, within a certain design space, which is first of all around the wheels here. So I'll pause this here. Around the wheels, we created a design space, and then asked the software, please do whatever you want. We just want lower drag. And then the software loops through a number of cycles where it calculates the sensitivities, which is information on the surface that tells you whether to push it in or out to achieve a certain goal. And then it actually goes to morph this. So the green that you see here is actually the displacement on the surface to reduce the drag. And what it's doing here is quite interesting. So they have designed the car, and the two wheels are external, right? And around each wheel, they had designed like a cover. And what's more logical than just creating a cover which is symmetric and pointing forward into the direction of driving, right? That makes sense. But what happens in reality is that the car itself is much bigger than the wheels. So, which means that even before the flow hits the car, it's already being pushed sideways. Which means by the time it hits the wheels, it has a lateral component. It's actually going outwards. So if then your wheel cover is pointing straight into the driving direction, but the incoming wind is going at an angle, you actually get like a crossing of this wheel cover and you get flow separation. So the software was telling us, no, you need to point these things inward at the front and outward at the rear, which is what you see here. We did the same at the rear wheel here. So here they had actually designed like a nicely smooth shape around the wheel, but in a 2D plane. So they made a nice like airfoil shape around the wheel. But flow is a 3D thing. So if the flow sees another path, which is easier to follow, it will actually jump below this 2D plane. And that created actually flow separation here. I can't see my cursor, but you can. It created flow separation around this corner. So the software was telling us, no, actually you need to add a round in the vertical plane as well. We did the same at the tail. This was an obvious one, but just nice to see. The software said, this is actual morphing, this is not just a gimmick. The software was actually morphing it and squeezing it and telling us you need to reduce the cross-sectional area that you leave behind, because this is a source of separated airflow and you're dragging air along. Now, altogether, we did this in 6 areas on the car, and we were able to reduce the drag by 15% on the car, which was already very streamlined. Of course, they then had to combine it with design aesthetics, obviously, cost constraints, manufacturing constraints, and so on. So it was watered down a little, but they still had 6 to 7% drag reduction left on their car. Then another example, let me just go back. I'll just go back and forth between these things. So those are the ways that we make it accessible to run simulations. First of all, running a simulation is super easy. It's all in the cloud, that you need in terms of preparation, hardware, software. And second of all, if you want to, our software can even do it for you. Now, one of the first questions we always get is how accurate is this? And of course, there are software packages which are more accurate because you get a lot more parameters to play with and you can really tweak it to your application. That is, of course, a given. But our mission is to be more than accurate enough to support your design, especially the conceptual design process, with simulations which are really fast to run. So some of the industrial cases that we have seen where customers have validated the results are, for example, Wingtra, which is a fixed wing drone. So a fixed wing is like something with a fixed wing flying forward and using the basic mechanics of lift to actually keep itself in the air instead of using propeller thrust. And they took their model to the wind tunnel, and here you can see the correlation graph. This is the drag curve that you see here. So as the angle of attack, which is the angle between the wind and the cord.
The aerospace engineers, they should know that.
Okay. Maybe I should. Okay. So angle of attack, and you can see the lift and the drag curves on these slides, which is a good correlation. We did the same for a very old Cessna airplane validation, which was done by NASA. So again, nice correlation. And this one is a fighter jet at low speeds because we limit ourselves to max 0.3. We run incompressible simulations. There you can really see the nice flow structures, the vortices arising at the top here, which help to generate lift in some cases, which help to spread the stall curve in some cases. So really nice to see this correlation. And we also do cars, obviously. A Tesla validation case. We got a full 3D scan of this car, and not just like walking around with your phone. It's insane what these guys do. A2 Mach 1, it's our partner. They take the car apart. They have 2,000 components, which they scan individually with super high precision scanners. You can even read the tire marks on the tires afterwards. They put it back together digitally, and you have like a virtual car to play with. And then they sell this to other car manufacturers, which is a funny business model. But we got this 3D scan, and it took the car to the wind tunnel, and we got the correlated too. And we had a delta of less than 6% between the measured drag coefficient and the one that we calculated. And it's not just about the drag value, it's also about the flow structure. So what you see here at the bottom is actually a slide of the total pressure, I think 10 centimeters or 100 millimeters here, behind the car. And you can see good similarities in terms of these four swirls or vortices coming off the roof here. There's a slight difference at the bottom. You see that this one goes almost tangential to the ground, this one does not. That's because we had a full moving ground, and they had only a moving ground, which is this white area here, just a moving belt in between the wheels, which means that it behaves differently on the ground. We also do CFD to CFD comparisons, which is the part here on the right. These are actually two different CFD simulation results. One conventional CFD package, and the other one is our simulation package. And of course, it's easy to make things look the same with coloring, but this is exactly the same scale, exactly the same setup, and so on. And then to discuss some of the cases that we've done. First, aviation. So this one is a pretty goofy-looking thing. It's a flying car. So it kind of folds all together, like the support struts and so on. It folds together. You can drive it like a car on the road. And then when you get to your airport, you can actually unfold all of these things, and kind of like a gyrocopter, it can take off, fly, and land. And they're using AirShaper all the time to analyze the drag for their yaw, for their pitch, but they're also looking at cooling because they need to cool their engine, whether they're flying or driving. So they're analyzing if anything up front is disturbing the flow and like degenerating the quality of the flow going into the side cooling inlets that you have here and here. So very interesting project, lots of aspects coming together. Then the one at the top right here, so what we have there is like a top-mounted propeller unit. Sometimes you see this on water planes, where you don't want water in your engine, for example. This propeller, we analyze the propeller, but this propeller actually generates a certain downstream wake, which then impacts the flow rate through the radiators that you have in the system. And I don't know if you can see it properly, but this here, this coloring here is the flow rate through the radiator, which is good in some locations and bad in other locations, and so they were able to actually optimize and modify the design. This one is again a fixed wing drone, Swiss company, and you see it has winglets already. So as in, you're an aerospace engineer, so you have to know this. Now I know this. The winglet blocks the flow, or partially blocks the flow, from bypassing from the bottom, which is high pressure, the pressure side, to the suction side at the top. They already had winglets, but by improving and optimizing the winglets using simulations, they were able to improve the efficiency of the drone, the entire drone, the lift over drag ratio, by 30%, which is a lot. It will not always be that much, but in this case, there was a dramatic improvement. They also built it, they tested, this one is now on the market, and they validated these things. This is one of the more exotic projects at the bottom right, one of the eVTOLs, which is electric vertical takeoff and landing vehicles. This is kind of like not a booming market yet, but a booming bubble, let's say, to provide a new form of transportation where you can just hop into a plane, lift off, go to some other place and land. I don't know whether it will become a true lasting market, but lots of interesting stuff happening there. And here we looked at if this thing starts flying forward, it's actually the opposite of what you want. So if you have a drone with vertical propellers, you have to tilt forward to tilt your thrust vector and to start moving forward. But that means this whole thing becomes a wing, but the wing generating downforce because it's actually tilting forward. So you want to be smart in terms of how to generate lift using the body instead of downforce when you're working on a concept like this. This one is not going to work, so I'll just go to this place. If I go back, I'm just going to mute. No, sorry. This one. Okay, good. Stop.
Looks like you.
No. So this was a very fun project. This is a modified Lamborghini. So the project was, the customer wanted the Lamborghini and the goal is 300 miles per hour. So just like any other goal. And that means you have to improve the aerodynamics because at speeds, well, anything at highway speeds or above, aerodynamics are the most dominant force you need to overcome. And the faster you go, the more important aerodynamics become compared to the mechanical losses. And so together with the designer of this project, we optimized the entire outer bodywork. And compared to the stock Lamborghini, we reduced the drag coefficient by 27%. Mainly by adding like a long tail to it, which really helps to guide and contract your weight. We added air curtains at the front. So air curtains are like channels in the front bumper where you take air at the front, accelerate it through a small channel, and then you spit it out on the sides to kind of help shield the wheels so that they don't act like a massive mixer. They will still do, but just to reduce the effects. Because you have to keep in mind, if the car is going 300 miles per hour, the top of your tire is doing 600 miles per hour. So kind of shielding that area is what you want to do. So this is the exit of the air curtain, which is a massive one on this car. We also have evacuation of high pressure air of the wheel wells. So as a wheel rotates, it's kind of generating high pressure. So we have this small slot here to push out some of that air. If we then move to the back of the car, they took off the mirrors for the record run. This is air intakes, so we want to optimize those, get enough air without causing too much drag. That's kind of an interesting balance. And then at the rear of the car, again, we have like the evacuation for high pressure air. We have some winglets at the top to generate some downforce, but not too much, because imagine this car generates like 100 kilograms of downforce at 100 miles per hour. If you go twice as fast, it's 4 times as high. So with the top speed car, what you want to avoid is that you just completely squash the car against the ground, because you're just going in a straight line. You don't need all that much downforce. Just a little bit to get enough traction is good. And what's very important is your aero balance, which is the distribution between downforce at the front and at the rear. Because if you put a massive wing at the rear of the car, you get all the grip you need, but your front is kind of not lifting, but doesn't have much downforce, which means you don't have much control over your car. And if there's one thing you want, like 300 miles per hour, it's kind of a bit of control. And we also worked a lot on the underfloor aerodynamics. And a big element of underfloor aerodynamics is the performance of your diffuser, because that massive expanding area helps to extract air and accelerate it underneath your car. So yeah, aesthetics are also important. So this is not the diffuser, this is just some bodywork. This is the real diffuser. And you can see that it opens up, it also goes wide in a soft way. And we played a lot in this case with the interaction between the rear wheels and the diffuser. Because if you look at one of the rear wheels, the air hits the wheel and then splashes out left and right as it hits the wheel. Sorry, and this disturbs the diffuser because this dirty air, this lateral velocity ends up in the diffuser and destroys your flow in the diffuser. So we played a lot with kind of shields between the wheel and the diffuser, air deflectors in front of the rear wheels to push the air down before it hits the wheel and so on. And if you're going 300 miles per hour, you need quite a bit of coolant on your engine. So the entire rear of the car is just an open grill to help evacuate air out of the car and so on. So that was quite a fun project. Stop this one. Yeah, I got a test drive for 2 seconds on the parking lot. That was it. That was my reward for this project. Then this one, what we also do is to kind of reverse engineer cars and actually try and understand what's happening with them. Wait, that's weird. Hey. Okay. It's autopilot. I don't know what's happening. Okay, that's better. Let's see, it's this one. So this is what I mentioned in terms of the reverse engineering. So this is the Rivian R1T, which is an electric pickup truck. There's quite a lot of Tesla competitors out there. And this is the 3D model that I mentioned. So this has been built based on up to 2,000 individual scans of components. They can just take everything apart virtually. This is the quality of the 3D scan, which is completely insane. And then we ran a simulation of this one. So you've seen the setup page by now. We set up the wheels and so on, blah, blah, blah. Let's just go through this. Ran the simulation, and then this is the output. And using a simulation like this, we were able to analyze what is happening in terms of the air curtains. So this is not a performance car, but it also has air curtains to help shield the wheels. And an SUV has massive and exposed wheels, so it's quite important to control the airflow well at the front of the car. They also have, yeah, this is what you see, flush door handles. So every small detail that disturbs the flow, try to make it as smooth as possible, just like Tesla is doing. Then you see the air curtains. You see the underfloor. So underfloor is also very important for aerodynamics because as the air travels underneath the car, or the car travels on top of the air, you want smooth airflow and a high velocity under there, so that when you get to the rear of the car, you kind of shoot it into the wake and you reduce the size of the wake that you leave behind the car. But if there's like all kinds of geometry, like on a conventional old car, you will see exposed drivetrains, your differentials may be sticking out, maybe there's like bolts and nuts to hold the car together. All of these things disturb the flow and change the aerodynamics underneath the car. So on modern cars, they put in a lot of effort to clean up the underfloor of a car and to make it as smooth as possible. So this is just a visualization of this 3D model. And then we reflected this in the simulation, so it's very smooth. Then we looked at the mirrors. One fun fact is that normally, because we run steady state simulations on symmetric 3D models, you would expect a symmetric flow. Now in this case, we saw that there was flow separation here at the top of the A-pillar, at the right A-pillar of the car. And we didn't see this on the left, so we thought, oh damn, our averaging is not working, we did something wrong. But then we inspected the model, and actually, we were able to detect like an error in the panel gap of this bodywork component. So it's actually quite a bit offset because it's an early production version. It wasn't perfect yet. So we saw some tolerance on the components of the A-pillar, and this resulted in an asymmetric flow. So that was quite interesting to get this as a feedback, that they had to optimize their panel gaps. What else did we see? Well, yeah, that was the panel gap, so you can actually see that there was an offset, which we didn't spot before. That was this. This is an air deflector. So this red bit here. So of course, cars need to be cheap to manufacture. So you can do this with a nicely curved shape, or you can just slap on like a vertical face there. What happens is that if this is the bottom of the car and this is your wheel, the air would hit the tire and then splash out, trying to go underneath, around, and so on. So if you put like a small flap there, the air ahead of it will kind of build up, and you form like a natural ramp, pushing the air downwards, which means it's already aimed downwards at the ground before it hits the tire, which means you kind of avoid the tire a bit and reduce this weight that you have. And it also helps to cross the gap of the suspension area, because this is again like an open pocket full of turbulent air going all kinds of directions. You want to reduce it as much as possible, the energy losses you have there. So that's the air deflector. You have them at the front. You also have them here at the rear of the car. And then this is what you see in the airflow. You can really see that the deflector pushes the air down, and the wake around tire, which is this bit here, is actually reduced quite a lot. We have the same at the rear of the car. Then we look at the air curtains. Yeah, so if you zoom in, on the 3D model, what you see here, if you look inside the car, so at the front bumper, you take the air in, and then there's this small channel going to the side, to the wheel well, and then it exits here via the side, and that creates this accelerated jet of air that helps to shield the wheel a bit. And then after it gets there, there's also like a small evacuation hole here behind the wheel. So some of that high pressure air from the wheel well, they try to channel it and then guide it via the sides here to help reduce the drag. And then what is cool on this Rivian car is that a pickup truck is of course not a very easy shape to work with, because you have the cabin and then boom, there's like an open space, and the flow just wants to separate and travel along a horizontal path. So what they did is to still have some control over how the airflow comes off the roof and close the wake as much as you want. They work with spoilers or wings, depending on how you want to call it, but this is attached to the bodywork, so I'll call it a spoiler. What happens is that if you look at the 3D model and you inspect the spoiler, first of all, it has a slightly downward angle to already guide the air downwards, to shoot down. And then there's also this hole. So it's actually a two-layer element. So they use this hole to shoot extra air down into the wake, and then the layer on top of that also is being pulled down to reduce the wake behind the car. The cool thing is that they also did something similar in the top view. So those side pillars here at the cabin, they're also slightly tapered inward so that they reduce the wake also in the top view. And those two combined actually reduce the wake quite a lot. And then of course it matters a lot whether your cargo bed is open or closed. That makes a big difference as well. We did some studies there. You can save quite a lot. So that's the top part of the car, and then they paid a lot of attention to small details. Even the towing system is like covered with a nice cover, so it's not exposed. But then go back. This is a more practical thing. So we worked with the Porsche Taycan model, and we had a lot of fun asking the garage if you can just play around with one, and they said yes, go ahead. So I asked some friends if they wanted to have fun, and we did.
Was that the sphere over there? You have a sphere? What is the sphere?
This one?
No, you show the sphere.
This one?
That one.
Yes, that is on how to curve a soccer ball. So
Here's doing the ping pong ball. So.
yeah. I was thinking of this one. So what we did here is we applied rotation to the sphere to see what the side force is.
Data? You have some data on it?
So if you want to curve a soccer ball, you have to apply a rotation to it, and this will alter the airflow around the shape, which means you get a different velocity at the two sides, which means, because velocity is related to pressure and vice versa via the Bernoulli's law, this actually generates a lateral force. So this video just illustrates in a very basic way how this effect works, and so on. So this is just a basic explanation. It's all publicly available. So the one working on the,
you have drag versus rotation rate, or
we did a few things. So this was a limited study. We just wanted to show non-rotating versus rotating to see what the difference is.
he's doing that.
Yeah. Then we can definitely share the video.
Yeah.
And the Magnus effect and so on. So just have a look through the videos. Another one I wanted to show is this portion. So first we went to the garage and explain all of the aero features. By the way, what's very important, if a car can have a low ride height, this usually is beneficial for the drag. So if you lower the ride height, you can lower the drag, and usually you also get better underflow aerodynamics and more downforce. Not always, but very often. So this one, what we did here, we just took some tape and applied some tufts, which is like small woven strands or threads, and applied them to the surface of the car because we wanted to validate what we did with simulations. So we had fun. Someone driving in this car, or the camera crew, let's say, which is just a cell phone, and then someone driving the electric Porsche. And then again, by analyzing the way these start to wiggle, if they wiggle a lot or go in reverse, that means your local surface flow pattern is not aligned with the main flow. We checked this and compared this to the simulation, so we ran a simulation. We could see in the simulation, what you see here is the surface friction. So the surface friction indicates the magnitude of the shear force that the air exerts on the surface of the car. If this is low, you would think, okay, then we have low surface friction. That is true, but the biggest drag comes from the pressure drag component. And if you have very low surface friction, this usually indicates that your flow has separated. And we saw this very clearly around the rear wheel wells, because as mentioned, these wheels act like a mixture, they create high pressure, and this splashes out on the sides of the vehicle. And we saw that we had nicely attached flow on top of the car, which we saw reflected in the tufts here at the rear. They're all nicely stable. Of course, there's always a bit of wiggle, but they're quite stable. And then we looked at what's happening around the rear wheel. So you see the wheel rotates, and this splashes out really like a massive disturbed turbulent cloud, actually, which you can then see reflected here. If we continue for just a bit, you'll see this reflected. Yeah, so the blue area is a separated airflow area. And then if you look at the car, you can see that these ones are really wiggling, sometimes even pointing forward. And the ones at the top, they are stable because they are still in the attached flow area around the wheels. So this is actually what we saw in simulation, and we saw the same in reality when we went out there to play around with the car. We didn't crash, that's good. Then we had the A-pillar vortex. So what happens if the air hits the front of the car, if the air hits the front of the car, it hits the windscreen, it can go up or it can go via the sides. But as the A-pillar is inclined backwards, it kind of curls around the A-pillar and then curls up along the windscreen, at least for this car. And then you see that locally, the streamlines are pointing upward. And that's what you see here. So locally, you see that the airflow is not just simply horizontal. These tufts are just pointing upward. I don't know if you can see this, but the front ones here, they're just pointing upwards. And then these swirls, these vortices, they probably go towards the roofline somewhere. And the cool thing is that you don't have to ask Porsche to do this. You can really just get out there. I would really recommend this to get some physical feeling with the airflow. Just get out there and apply this to your own car, which is what we did as well. This was an illustration of how we can do this and apply vortex generators to your car. So we played around with the Volkswagen Beetle, fun car. and applied some tufts to it just on the rear windscreen. Because even though it looks aerodynamic, it's actually not aerodynamic at all. And there's like edges here right in a very critical location, so the flow kind of trips. And we saw quite a lot of detached flow and movement of the tufts at the rear window. So we thought that might be interesting to add some vortex generators. Now, a vortex generator comes in many different shapes and forms. What we did is just to place two vertical elements there and put them under an angle. So I'll do it like this. So if the flow comes in like this, if it's just aligned with the flow, it just passes over, nothing happens. But if you put the plane like this, it hits this side, high pressure and low pressure here, which means it wants to curl on top of this. And as it curls on top of it, it jumps down afterwards. And if you do this with two vortex generators, you get two curls jumping down and joining forces. And this, what it does is that it takes energy from the free-flowing air and injects that momentum into the boundary layer and helps to actually attach the airflow onto the surface of the car. And the cool thing is that when we went out there and tested this, there's a fantastic explanation of vortex generators. What we did is we just, with some duct tape and a bit of wooden beams, we applied the camera to the back of the car, and across a span of maybe 3 to 10 seconds, we looked at how much the range was, the movement range of the tufts was. And we plotted this for the two setups, with and without vortex generators. And here you can see the difference. So without vortex generators, we have the red. So that means that this tuft saw every angle it could possibly see. This one as well, this one as well. And then the green is actually the same with the vortex generators. And you can really see that this spread in movement was reduced by quite a lot for most of the tufts. So especially the ones right after the vortex generators, where the flow would actually be pulled down and energized. So I would definitely recommend that you just start playing around with this. I've seen a lot of models here, which Joseph showed me with vortex generators, with tufts on them. So there's a lot you can do yourself. This one I will skip, but instead I would recommend that you just go to AirShaper, click sign up. The accounts are free, and if you then go to projects and sample projects, you can check out all kinds of sample projects. There's a Tesla Cybertruck, there's remote control cars, there's drones, there's hypercars, there's tuk-tuk if you want. There's anything you like. So just to compare flows of different elements, yeah, this is just a video page. We did our best to kind of cover quite a lot of topics. Yeah, golf balls, spinning soccer balls, but also MotoGP aerodynamics. There's an interview with Professor Katz in there. That's 4 years old, I think, already. We did work on Porsches. We're also working on Pikes Peak. I don't know if anyone knows the hill climb race, Pikes Peak. Robin Shute is now the record holder. He's using AirShaper now. And what we did with him, and I got to visit him like last week, or this week actually, he's changing his Pikes Peak setup to a setup for the track. Because at Pikes Peak, you have very low air density as you go up. Completely different setup, completely different needs. So he's now changing his setup using AirShaper to change the rear wing, to change the number of elements he has on the wing, and so on. And he ran a first test. The only thing he needed to do was change the flap 1 notch. That's it. Other than that, there was good correlation with simulation. He went out there last week and he already broke the lap record at Willow Springs. Slashed it by 11 seconds. Quite dramatic. And this weekend he's going to go after the Laguna Seca raceway record, which is now tied to an IndyCar, I think, at the moment.
Was that Big Willow or Streets of Willow?
That I have to check.
Okay.
Yeah, I have to check. I don't know by heart. So if you want, you can stay tuned or go there if you have the time. And yeah, as I said, just go to app.airshaper.com, make an account, and just look at the sample projects, and that's it. And yeah, there's some more fun videos coming up. I had the chance to go to NASA 2 times last 2 weeks, Ames Research Center and Edwards Air Base. So there's more stuff coming up if you like the videos. And that's basically what I wanted to tell today. So thanks a lot for listening. Questions? Shoot. Yes.
Do you have a student license for this or anything?
Not yet. The only thing that we do have is a Formula One in schools license. So that's kind of a fun discipline where they have like pressurized cartridges and just shoot their cars. It's really nice. That's the only thing we have at the moment. But we're discussing with NASA if we can kind of support students throughout America through NASA with the credit package. So we're looking into this. So if you like that, you can help support the initiative.
All right.
Yes.
Was that modified Lamborghini able to hit the 300 mile per hour mark?
We're on the way. The first test they did, the goal was to hit 420 kilometers per hour. I don't know by heart how much that is in miles per hour. And they hit 447 already, which is quite nice. They're now rebuilding it. They found that the nose was a bit light at 447, so we played with a bit of dive planes at the front and looked at the front splitter and changed those two little wings that we have at the back. They're now building this and they're going to go out there to test again. So hopefully.
Yeah. What kind of turbulence model do you use for this simulation?
Yes, everything is steady state RANS based. We use K omega SST, which has its drawbacks and its benefits. The drawback, of course, is that we also don't use prism layers. So we use turbulent wall functions, which is a simplification of reality. But the benefit is that you can spend that mesh more on surface resolution and volume resolution rather than on prism layers. Plus, our platform is a general purpose platform. Sorry. So that means it needs to work for anything and anyone working with it. And if you want to add prism layers, that's quite challenging to get it to work. And the wall functions, they do add some stability and robustness to the simulation. So that's what we use. So it's a blend between cost, accuracy, and speed, which is quite interesting. Yes.
So you said in the beginning that your program values itself on time. You know, you use a finite number of like nodes for each, or the same mesh, I guess, a special number. But if you're analyzing things from, I saw on your YouTube channel, you have everything from a golf ball out to like a Lamborghini car. Those are different size models. So
Yes.
does your program just create a much finer mesh for something like a golf
Yes.
ball? And in that case, I was going to ask, but you don't have to answer right now, obviously. But what would the cost be of your simulation, of one simulation? I mean, would you feel comfortable disclosing that, or is that?
Yeah, that I cannot disclose because that is quite confidential. But even on our end, the ratio between different simulations can be a factor 10 almost. Because one simulation can run for 5,000 iterations and another one can be done in 600. Which means we need a very big balancing exercise because if they all go for 5,000, we're bankrupt. And if they all go for 600, well, they're just overcharging people. So that's the balance that we have. To answer your first question, what we do is we have that budget of 10 million cells, or 1 or 100 million cells, and we stretch it according to the size of the object. Which means that in case of a golf ball, yes, in terms of absolute cell size, you have very, very small cells. Might still not be enough because it's very complex. But in terms of a car, for example, with so many features and like these air curtains, they're so small, you need to fit mesh inside. It may not still be enough. May still not be enough.
That's
So,
what you use your adaptive mesh.
Yes. Yes.
Thank you.
Go ahead. Yes.
Like for rotating propellers and tires, what kind of mesh setup do you use? Like, does the entire setup along with the mesh rotate, or is it just that?
No. We run steady state simulations. We know how to do this manually, but again, we would have to charge customers way too much because if you have a sliding mesh interface, a rotating mesh interface, that just per definition means you have to go to a time-dependent simulation or transient simulation, which means factor 10 at least in terms of computational cost. And that would not be profitable anymore for us, and people would just say, no, for that money, I'll just get a license and do it myself. So what we do is we use the moving reference frame, which means that we do create a specific mesh around the propeller. And within that mesh zone, which is a cylinder that we create around the propeller, we add extra mathematical equations, which take into account centripetal forces, Coriolis forces, and those help develop the flow around the object as if it were rotating. But it's not actually rotating, which creates a funny situation because the position of the rotor versus, imagine this is the arm of a Joe, if your propeller is like this or like this actually has an effect because it kind of calculates the instantaneous flow pattern around it. So if you're on top of the support arm, you're just pushing air on top of this one. And if you're like this, you just have the free airflow. So sometimes we have to do 2 or 3 different positions to kind of take an average of this. Other questions? Yes?
I'm looking at your GitHub, and you mentioned some open source thing you had.
Yes.
It's called adaptive mesh refinement.
Yes.
Is that just so that's just data? So it looks like you're using OpenFOAM, right? You mentioned
Yes.
that before.
Yes.
And do you just use the like my basic understanding of OpenFOAM is you have like the CF mesh, snappy hex mesh, and I don't know, maybe other things.
We use Snap, yeah.
It says that right there. And do you use that for your mesh refinement pass, I guess?
Yeah, the thing is that we use Snappy Hex Mesh, but the adaptive mesh refinement that we wanted is not available. Because in OpenFOAM you can refine and even unrefine cells, but only volume cells. If you refine cells which are close to the surface, if you have a sphere, for example, the sphere becomes like a discrete representation cut by the cells. It's all lines. If you refine a cell which is close to the surface, you cut it in half, but you don't go back to the original surface and increase that surface correlation. You just refine the cell that was already there, which means that line, or those lines on the circle, you just cut them in half, but they stay the same. What we did is that we changed the entire system so that we go back to the original 3D model and find better correspondence to it with the refined cells. That's what the library does. The convergence detection is also in there, so you can apply it. And I think we use the motorbike tutorial case for the adaptive mesh refinement. Of course, our version is a bit more advanced, and we do multiple loops and so on. But you can definitely play around with it.
Cool. All right. Appreciate it.
You're welcome. Yes.
Is there a way to link dimensions in your CAD program to AirShaper so it can run through a variety of different ride heights, pitches, wing angles, stuff like that? Or do you have to individually have the files and just load them all in for a bunch of simulations?
For now, it's individual files. There's pros and cons of doing this. The pro, of course, is that you can stay nicely in your environment and say this parameter is tweaked from 0 to 10 and just run. That's nice. But the downside is that you're CAD software dependent, which means you have to write a plugin for SolidWorks, for Creo, for CATIA, for anything. It becomes heavy quite a lot, and we're still a young and a relatively small company. So we chose to go the other route, which is the optimization that I showed you. We just work with STL files, STL, step, and object, because those are universal file formats. Now, it's quite funny because those are, these are really nice formats. The people developing them are intelligent, but the file itself is without any intelligence. If you export a sphere, it's just a collection of triangles. The model itself doesn't know, hey, I'm a sphere. And if you upload it to a software, the software doesn't know it either, unless you have like a fitting algorithm. So we actually chose the hard way, because if we want to set up rotating wheels or propellers or anything, we have to do it based on geometry, which doesn't tell us that this is a propeller or that this is a wheel. So when I showed you that we can detect wheels, that means we had to create algorithms to automatically analyze that, oh, this is a wheel. And we had to make software that analyzes this is a propeller and this is a central axis of the propeller. Just to provide that ease of use to the customers and still be compatible with any software out there through that universal file.
Okay, my next question will be, we've run some safety simulations of the FSAE car.
Yes.
And we have the tires, set into the ground slightly.
Yeah.
If we were to use AirShaper, would you want the tire directly above the ground plane, or do you want the squish into the ground plane?
You have to cut it.
You got it?
You just cut it. And if you really want, you can actually model the deformation of the tire.
Yeah.
Then you're actually going into the details. But yes, you have to prepare the model. What we do is we just snap it to the ground, and that's it. Other questions? Yes.
You just mentioned you guys use STL files, but do you guys also use DAT files?
No.
No, just
not
STL.
Yeah, STL, object, and step.
Okay.
Yeah, so all 3D file formats. Yes.
Step files. So, do you? I guess my comment was. So you said that you after you run the simulation, do you mentioned that you give people the mesh and
Yes.
those files as well. So could you like, I don't know, could you run those files?
Not straight away. That's kind of a bridge too far for us because then we're just saying, okay, do one simulation and run the rest on your own.
Yeah.
You could do it if you're quite knowledgeable on OpenFOAM. You can try and reconstruct all of the folders that you need. You could do that theoretically. But actually, we wouldn't mind too much, actually. But then anything you change in terms of geometry, you have to remesh it. So the only thing you could do is run a different turbulence model, different speed, for example, those kind of things. Yeah.
Cool.
Yes.
I guess for the model that like you were able to change the shape based off the drag that was there, what did you use for that? Was that just like something that you created, or?
It's called adjoint shape optimization. So what happens is that if you have a car, if you want to reduce the drag, theoretically, for every point of the mesh, what you could do is just pull it outward a bit and rerun the whole thing and see did my drag go up or down. Second node, pull it up and down again. But there's usually a few million of those points. That would mean a few million full simulations. But there's something called adjoint, an adjoint simulation. What happens is that you run your base simulation, so you just run a normal aerodynamic simulation, which is called the primal simulation. And then you run the dual simulation, which is called the adjoint simulation. And this one calculates all of these gradients in one go, which means for every point on the surface, it will tell you, this has to go out, this has to go in. And if you bundle that information, you get what is called a sensitivity map, which is based on these gradients on the surface. And that map you can then use as input for your 3D morpher, which will then actually execute the suggestions of the sensitivity map. And once we have that model, you can go back, run the primal simulation, run again a dual simulation, and get sensitivity maps, and again do the morphing. And if you then loop through a number of cycles of that one, which in the end is maybe 40 simulations or something, then you end up with a morphed model. And then we send the morphed model back to the customer as an STL file, so they can load it into their CAD package and replicate the shape with their own software. That's how it works. Yes?
So I think based off what you're saying about kind of like the morphing, how it kind of does it for you, how you want this node to go up, this node to go down,
Yeah.
and actually automatically does it. Have you ever had any problems with that algorithm producing invalid geometry?
Yes.
Or, like folds in on itself or something like that?
Yeah, so there are limits to this method because the morphing that we do it directly on the CFD mesh, actually. That means that the surface itself can actually be weird, but that is kind of okay because what we do is we create like a control volume around the area we want to morph, which is then divided into separate discrete points, and then we have kind of like a spline morpher inside. So the modifications are quite gradual. It's not like each node on its own is trying to morph. That happens, they try and implement this, but exactly because of the reason you mentioned, it's very difficult to get that right. Because very often if you have like a smooth surface, and then every point gets to move around on its own, you get something like this over time. So using this spline morph, we kind of filter out the weird effects, and we avoid like this self-collapse kind of effects. The problem is though, because we morph the mesh, if you morph it too much, your cells go from nicely squared to kind of very skewed, and then simulation goes up. So there are limits. Other questions?
All right. Okay. Thank you very much.
You're very welcome.
Yeah, I mean,